So I'm going to just get on it because I have lots to say. So we have a problem. Who is we? Well, we is biblical young earth creationists, flood geologists. What's the problem? It's a heat problem, and it's the heat associated with accelerated nuclear decay. So I had an idea that I chased of a way possibly to solve this heat problem, and it was published in Creation Research Society Quarterly last fall in consecutive issues, summer and fall, parts 1 and 2. And latent heat could solve accelerated nuclear decay's heat problem is the title. The title's long, the papers are long. Prior to that, I went on an exploration of the radio halo and its relationship to accelerated nuclear decay. Wrote a couple articles for RMCF in the foundations, and also a parts 1 and parts 2. So I think probably copies of these are still available, maybe. So I also have preprints or copies, PDFs of my papers in CRSQ out there as well. I am going to say as little as possible about motivating why accelerated nuclear decay is necessary, because that was the content of my previous talk here and the papers for foundations, and try to move on to the heat problem and latent heat solution. So we have a heat problem, and regardless of how accelerated decay of radioisotopes happen, we have a heat problem. Regardless of how the radioisotopes found themselves in the Paleozoic and Mesozoic granites, where many have been cataloged, namely thorium, uranium, polonium inclusions of radioisotopes. Regardless of how they got there, regardless of how granites formed, regardless of your preferred flood model. And the heat problem is especially apparent for and constrained by radiohalos. So we will see some of them. We already saw one on my front slide. There was accelerated cooling as well. And this is not something maybe everyone thinks about, but you can't have one without the other. And so the problem is, what was the mechanism for it? It must have occurred. The heat, the excess heat from the rapid accelerated decay of radioisotopes had to go somewhere, or else it's not a rational model. So this is a polonium-218 radiohalo, the cross-section of it. These things are on the order of tens of microns in radius, so that inner ring that corresponds to the emission of an alpha particle from polonium-210 is at a 20 micron radius. Just to help you get there, I've got on the one side, for scale, a penny next to a couple of samples of granite with mica, and in the mica, or the biotite, is where these inclusions of uranium and then mainly the uranium and thorium in there, and that's where you would find these radiohalos. On the top right, there's just a large crystal of biotite with a coin for scale also. So radiohalos, they're ubiquitous, and particularly ubiquitous in granites. So I have just a picture there on the left of some granitic rock. It's pinkish, it's a big pluton underlying sedimentary strata, and radiohalos would be in there. Also, I show a dike on the right of how one might associate granite, magmatic rock, with strata. It's because they cross-cut, and so if the magma, when it was molten, plumed out above or went laterally, it would be a sill of granite that would be there. And radio halos could then be associated with the geologic column according to where you are in the strata. So on the right, I have a geologic column. Just the Paleozoic, Mesozoic, and Cenozoic is shown there. And these are the samples, units and samples that were pondered in great detail with counting of radio halos in the, by Dr. Snelling and published in Radioisotopes and the Age of the Earth, Volume 2. So you can see very high counts of these halos. The radio halos are named by the source in the middle of them, the radio center that's generating the spherical shells that in cross-section give you rings. So there were also radio halos found in Precambrian granites. So now you see the same geologic column on the far right. I'm making certain I'm oriented on the far right. And then the geologic column linearized with time, which of course is humorous because all of that Precambrian would have been associated with Creation Week. But just to have a place to list the samples and the units, rock units where the samples were taken in across various levels of the Precambrian granites. And just accelerated nuclear decay was necessary for many reasons. Just explain what we see in the rocks, but there were likely more than one episode, and there would have perhaps been an episode on day 2 when the dry land appeared and a lot of geologic work was done, and that would account for the radio halos found in the Precambrian rock, the basement rock, pre-flood rock. And then the rest is flood rock, and there would have been an episode of accelerated decay during that year of the flood.
Just to the left, because you're blocking
I am. What am I blocking?
with your shoulder. The screen. Perfect.
Okay, very good. So we're forming a halo right now. Pixelated would have been better, but this was my option in PowerPoint. So the halo forms as alpha particles, the source that is emitting alpha particles from the middle, and it's isotropic but random, and makes a little burn scar at various radii according to the energy of the alpha particle. Basically, the halo would have formed with the switching on of accelerated nuclear decay, abbreviated A and D there, and off. Or if the source were depleted, it would also quit, and the halo would quit forming. So the source nuclides at the radio center, if it's a polonium-2 18 halo, is polonium-218, but it would probably be in a compound aggregated at a site per the transport model due to Dr. Snelling, and so maybe polonium sulfide would collect. And so the source nuclides are actually morphing through the uranium decay series, only it's just the tail end of the uranium decay series for the polonium halos. And there are 3 types of polonium halos. Polonium halos with 3 rings, that's polonium-218, 2 rings, polonium-214, and 1, polonium-210. And then the uranium halo includes 8 rings, though some of them are on top of each other, so it looks more like 5, for all the alpha particles in the uranium-238 decay chain. And it's important to realize that each ring represents from 100 million to 1 billion emissions in order for it to show up as a ring. They can also be overexposed, and then you wouldn't recognize them as a halo either. So split the difference, 500 million emissions per ring. So here's a uranium halo for you, appearing. Its source is shining, meaning alpha particles are emitted, and then accelerated nuclear decay is turned off. The uranium falls back to that really slow decay rate with its 4.5 billion-year half-life, and so it's effectively turned off. And then the source nuclides in this case are uranium-218, and you can see the number of rings there. There's a very, very faint ring all the way out at the same, I tried to scale them, radius or diameter as that polonium-218 halo I showed. And it morphs through the decay series until you reach stable lead-206. If it were a thorium halo, it morphs through until you get to lead-208. So, according to Dr. Snelling's transport model, the only way we can have polonium halos is if they form simultaneously with uranium halos, and the whole thing was accelerated to where you would get a halo in something like 5 days while accelerated nuclear decay is on. So this would be, this shell, this blue cage, would be like the three-dimensional version of the polonium-210 halo. And you can imagine three-dimensional high-speed Russian roulette with a gun swinging around, firing, firing, firing. The bullet comes to a stop at a characteristic stopping distance, which is the radius, and it heats the rock up, and it makes a scar. It discolors the rock, and that's what the halo is. So there's no way around the fact that heat was generated with the formation of radiohalos. This is another way to picture it with the linear energy transfer on the vertical axis, and it peaks at these, try not to puff so badly, it peaks at these, the radius, what would be the radius if it were not just a linear analysis. And so the little flames indicating where the heat. Just interesting that the majority of the heat is deposited right where the bullet, the alpha particle, stops. And that's why you get a ring. Here just shows the uranium, part of the uranium-238 decay chain. I truncated a little bit, so uranium-238 morphs through with a few alpha and beta decays. You get down to radium-226 and then radon-222, which is the gas that, according to the transport model, escapes the zircon and displaces the rest of the halo, so that the polonium halos are effectively daughter halos to the uranium halo. There are 3 alpha particles with the arrows associated with polonium-218. That's why the 3 rings. The Q alpha, that would be the energy associated with the alpha emissions, and it's about 20 MeV for polonium-218 halo, and that's really the main point of this slide, but also it's a ba-ba-ba. You have the consecutive decays of the alpha particles, first, second, third. It's the middle ring, the outer ring, then the inner ring, and so, but each one could go in a different direction, but there's enough going off from the radio center that it fills out the spheres to give you the shells, the concentric shells. There are also beta decays, but from the standpoint of, this is my little heat analysis, or temperature, adiabatic temperature rise as an approximation. The betas are the electrons that come off when basically a neutron and flips over to a proton with the emission of an electron. And so but the beta particles don't carry as much, they're not fired off with as much energy, they travel much further being small and light, and we're neglecting their heat contribution to the environment. So that, again, the heat it's like a friction, these things are coming to a stop, the heat is deposited near where they stop and discolors the medium. And we're ignoring the electrons for this analysis. So an adiabatic temperature rise would be a pretty good approximation in this rapid accelerated nuclear decay scenario, because the heat can't dissipate from rock that quickly. And the formula is just the energy, the Q, divided by the mass times the specific heat, rho V is the mass, and then the number of alphas, that 500 million, 5 times 10 to the 8. And so there's some numbers for biotite's density, the volume of that farthest out ring, of like a little sphere, and the specific heat of biotite. You can do some quick calculations. And for a uranium halo, we're talking about a temperature rise of, these would be minimum numbers. And I think 7,600 degrees Celsius for the polonium-218 halo, 3,400, and for the polonium-210 halo, 900. The import of this is that radiohalos anneal away if the temperature of their environment is greater than about 150 degrees. And then the biotite itself melts at about 600 degrees. So radiohalos, they make a heat scar, heat is generated, they could not survive their own heat. Not even if the granite started out at absolute zero, the temperature rise still will exceed the melting temperature. So the reason for this radiohalo walkthrough is that halo formation motivates a logical or suitable model for a cooling mechanism. I already have said it requires accelerated nuclear decay and also accelerated cooling, but what is that mechanism? Well, the cooling has got to be local, immediate in the vicinity of the radio center. It's got to be commensurate, or else you're not removing enough of it, and you'll still be too hot and the halo will anneal away. And then it has to be contemporaneous. It has to be at the same time. And so these details, what kind of model will work there? Well, let me just point out that Dr. Russell Humphreys published in 2018 a new mechanism for accelerated removal of excess radiogenic heat. And I don't want to take the time to explain his model, except to say that the temperature that granite experiences in his model is too high for radiohalos. It's not good enough for radiohalos. 300 degrees Celsius would be the temperature, that's the green dashed line. He's got heat loss on the vertical axis and temperature, Kelvin, which I translated over to Celsius, on the horizontal axis. His model is a venting of heat through a hypothetical fourth dimension by total internal reflection of black body radiation. But it's not good enough for halos. And it has that hypothetical fourth dimension that does not sit too well with me. But maybe. So what if? And this is where my mind went with the idea to solve the heat problem. What if the radio center itself were a heat sink? Think like a drain. During accelerated nuclear decay. Continually taking heat from its environment, which is the halo region, as each decayed nucleus changes phase, liquid, solid, gas, phase, reverting to its usual higher entropy state at decay series end. When something fundamental changes and you go from a unstable nuclide to a stable one, to lead, or until the source is depleted or A&D is shut off. So think of ice cubes in a glass of water. The ice changes phase from a lower entropy state to a higher, and as it melts, it's a fixed temperature, but it's pulling heat from its environment, the beverage, and keeps it cool. I mean, it's fighting against ambient, especially if it's in a glass and not in a some kind of vacuum. And once the ice is gone, of course, your beverage will get hot. Of course, it's diluted, but diluted. But never mind. So that's the idea. It's the nucleus itself. We're talking about changing phase. The nucleus. So here's another picture of it. There's our polonium-218 radiohalo from Dr. Gentry's book jacket. And the red arrows are representing the pull, the sucking of heat into the radio center, and then the three white arrows are that up of the 3 alpha particles in a given decay, going off wherever they go, isotropically, randomly, spherically. So if we put it with my little animation, then the heat's coming on, the alpha particles are going, everything turns off, radio halo is left. Because enough heat was taken away, after the scar was formed, because cooling it doesn't undo the scar, it's heating it, annealing it away, not cooling it. So that's my idea. But how do I get there? How do I substantiate this? Well, just a reminder of phases of matter, right? Gas, liquid, solid. And there's a latent heat associated with them if they're normal or first order phase transitions, like with water. Removing heat effects brings about the phase change and lowers the entropy without changing the material's temperature. That's the material inside. That the environment is cooled by sucking heat into the ice cube that's melting, which would be like the nucleus, the lead nucleus, you might say, is melting, just to borrow from that analogy, though it's an unknown phase is all I suggest in my papers. I don't say that the nuclei during accelerated nuclear decay is a solid. So you can sort of think of accelerated nuclear decay, an episode of it like an AU, where, and I'll touch on this, right here, that there's a change in the physics of the cosmos that God would bring about. So here are my assumptions for could latent heat solve our heat problem. I'm assuming accelerated decay is the result of a change in the strong force, God tweaking his gluons, causing an episode of AND during flood deposition. And all of this is per Dr. Chaffin, Eugene Chaffin's work in Rate Volume 2. I'm also assuming that granites formed as molten rock or magma cooled, at least the ones that hold radiohalos, which also expelled a lot of water. That's part of the crystallizing process, and that drives the transport that gets the slippery radon out of the zircon to displace the polonium so that you can have polonium halos separate from uranium ones. That's all per Dr. Andrew Snelling's work, also in Rate Volume 2. And then the zircon grains that house the uranium inclusion get sandwiched between leaves of mica, which crystallized from the melt. Okay, so assumptions. Now, my ifs. If the nuclei of heavy, unstable nuclides, like uranium-238 and thorium-232, are in a lower entropy phase than usual during AND, this AU time, which is due to God altering the strong force which accelerates decay. That's the first if. And I would assert that the text argues, from Genesis 6, argues for divine intervention here, where we see in time God observing the wickedness of man and declaring that he would judge, and his regretting he'd made man on earth, that this is a judgment brought about by God miraculously, in my opinion, so to justify this gluon tweaking. Second if there are no thermodynamic considerations associated with the miraculous change, the accelerated nuclear decay change and the strong force change, and that the nuclei just find themselves in this lower entropy unknown phase or state. And here I would point to another miracle, the raising of Lazarus. There were probably no thermodynamic considerations, big temperature changes in the cave when Christ said, Lazarus, come forth. So that was a huge change, entropy, change in state. It's information entropy instead, perhaps with the DNA, but it's an example. It's a gospel miracle instead of a judgment miracle, but even so. So those are two big ifs. And then the biggest if is the last or the biggest point. If the decaying nucleus undergoes a spontaneous endothermic first order phase transition, once it becomes lead-206, and there's something fundamentally different about stable lead-206 than all the preceding nuclides in the chain. Or, I mean, if that's for the uranium series, or lead-208 for the thorium. And then, and that's at the point when it abruptly ceases to be unstable. So this is like the ice cubes cooling a beverage and melting. So some of you are saying, what are you talking about, the phase of a nucleus? Well, if you've taken nuclear physics or chemistry, whichever one you want to call it, there is a very famous thing called the liquid drop model of the nucleus, which is very successful. And in fact, the nucleus is considered to be condensed matter, which is sort of code for liquid. Solid state matter is code for solid. So there I just have a pretty water drop on a leaf. So the larger deformed nuclei like lead-208, lead-206, uranium-238, and so forth are not exactly spherical, but and there's a skin that's been discovered on the surface of the nucleus. But in any case, the liquid drop model describes nuclei extremely well. You just get a radius, this number times the mass number raised to the 1/3 in femtometers. That's the sort of scale of dimensions for nuclei. And the nuclides form, you put the element name and then precede it, superscripted by the mass number and subscripted by the atomic number. And the neutron number is greater than the proton number in these kinds of nuclei. But I saw an article that said what the nucleus was mostly like is a truffle. So it has a skin on it. You might have to have two types of chocolate inside though, because it's neutron heavy. So the skin is neutrons and there's kind of a core of neutrons, and then the mixture of neutrons and protons would be between them. So the neutron skin has been confirmed by experiment and measured for lead-208, and that was just like year before last. And it's got a 0.28 femtometer skin and 5.51 femtometer radius, kind of amazing. Also, nucleon pairings, like pairs of neutrons, pairs of protons, a neutron-proton pair, which is a deuteron, have been seen, in as much as you can see anything in the nucleus, by scattering experiments now. And not only that, but alpha particles have been seen near the surface, that energetically near the surface, which there has to be because that's what decays out. If you switch models from the liquid drop model over to the quantum model, semi-classical model with an alpha particle tunneling out. Okay. And it's just, these are finite systems, so you have to be a little careful. Bulk behavior that we think of with phases doesn't quite apply. These are very finite, and so each isotope, if you're going to do a phase, model it and do a phase diagram, do molecular modeling, which is where I would like to go. Anyway, you would have to, you would get a different answer for every isotope because the number of nucleons is different. So it's not impossible that this alternate phase, in my opinion, could be a solid. I call it a femtocrystal instead of a nanocrystal because we're talking about tens of femtometers for the size of the nucleus instead of tens of nanometers for the, the nanocrystals that are all in the news. But alpha nuclides, which are just multiples of alpha particles, have been modeled as solids relatively successfully. So that's interesting. So like helium, beryllium, which happens to be unstable, that's kind of weird, and we'll come back to it. Carbon 12, so it's helium, beryllium 8, helium 4, carbon 12, oxygen 16, and then you get up to calcium 40, and then after that, the alpha nuclides are all unstable. So what are the particles in our nucleus? I call this stuff nucleum because I think it's cute, but what are the particles in it? Because you have to know what the particles are if you're going to go model it. You just kind of like to know it if you're doing quantum mechanics. What are the quanta? So there's a nuclear shell model out there too where you have the neutrons in a neutron well, the protons in a proton well. They're side by side. The proton well has a Coulomb barrier that you tunnel out of. Neutron well doesn't, so you might have resonances above it. But the nuclear shell model does really, really well predicting magic numbers, which are like the magic numbers in the periodic table too that correspond to the noble gases. But anyway, does really well. But then an alpha particle model is what's used to model the decay of radioactive isotopes. And it does extremely well. You have to throw in a fudge factor that's like a probability of how easily pairs of neutrons and pairs of protons can get together and be an alpha particle so it can tunnel out. But order of magnitude, it does really well. I think it was Gamow who got the Nobel Prize for that. So what is it? Is it an alpha particle? Is it a neutron and a proton? Is it pairs of neutrons and pairs of protons? So this is what I've decided is most like. It's most like cation and anion, where the neutrons pair up by Pauli exclusion principle, they stick together. Protons pair up. The pair of protons would be like the anion, the pair of neutrons like the cation, it doesn't matter which. And so if I want to borrow an analogy to figure out a latent heat magnitude, how do I do it? I have to go to molecular systems. So a molten salt in just monovalent, like sodium chloride. There's a lot of data out there for sodium chloride, so that's what I went with. And so when you have liquids, molten salts, vapor salts, so it's a fluid, you get temporary pairings, dimerizations, and when you realize when you pair up a neutron pair and a proton pair, you get an alpha particle. There's pretty much consensus that the nucleus is not a solid, but I think it's an open question for during accelerated nuclear decay that maybe some of the nuclides might be in a solid phase. But in any case, there are different phases of liquids, lower LDLs and HDLs, low density and high density liquids that transition from one to the other. So it could be a phase transition between two different liquid phases. But you can count how many neutron pairs and proton pairs you have across the pink there. I show U-238 has 73 neutron pairs, 46 proton pairs. Polonium-218, 67 and 42. Lead-206, 62 neutron pairs, 41 proton pairs. And just to remember that there's a strong particle number dependence, which means we have a different phase diagram for every single isotope's nucleum, if you like that term. So one question is can I find a liquid-liquid phase transition in a modeling by molecular dynamics, a system where that phase transition has a latent heat? Or liquid-solid if I would argue for a solid phase. But my analogy back with sodium chloride, so there's liquid and solid sodium chloride depicted in the cubes on the left. And so I just made a little ratio. Latent heat of melting per formula unit for salt compared to its lattice energy is equal to the latent heat per alpha for a nuclear phase change divided by the alpha particle's binding energy. If you do that, you get an enthalpy change, which is T delta, temperature times entropy change of about an MeV. I go through a few different scenarios in my papers, but one other is it might be appropriate to subtract the binding energy for two deuterons, which is the closest approximation we have of what would bind neutron to neutron and proton to proton in the nucleus. Subtract that from the denominator on the right, and then you get a little less than an MeV. But so this then made me very, very happy, because if you look at uranium-238 and you have the side-by-side neutron and proton wells, you have a neutron core at the bottom with 21 neutron pairs. Then you have 41 neutron pairs, 41 proton pairs, which are just wannabe alpha particles, really bad. And then you have resonances on top, which represent all of the alpha and beta particles that decay until you get to lead-206. So that's the uranium halo next to it. look at the Q alpha for uranium again, it's 43.7 MeV. How many, and it's about 1 MeV per alpha particle by my analogy, and I have 41 neutron pairs and 41 proton pairs. So it's a match to remove about the same magnitude of heat, 41 MeV, 1 MeV per alpha particle. Each neutron-proton pair makes an alpha particle that's comparable to the energy from the alphas emitted from the radio center. So I thought this was really very exciting. So modeling this on a computer, whether Monte Carlo or molecular dynamics, might involve a potential that looks like this Stillinger-Weber potential, which includes a pairwise term and then a many-body term. And there's a parameter, it's shown as lambda, between the two parts of the potential that ends up entering the phase diagram as an axis. And so what this would mean is that parameter would be what changes when you switch on accelerated nuclear decay, because it's parameterizing or characterizing the change in the strong force. It would be made shallower. Naturally, things are going to spill out faster and you're going to decay quicker if this nuclear force were weaker, shallower potentials. So this just, again, gives me a very specific, though I still haven't done it because I need some questions answered, thing to model to explore my theory. So this is the very famous average binding energy per nucleon curve against the number of nucleons. And it very quickly, as you put nucleons together to make various elements of the periodic table, it climbs up and flat tops. That flat topping, which says your volume is proportional to the number of particles or number of nucleons, is one of the giant justifications for calling the nucleus a liquid or condensed matter. Notice the helium peak, which is the inset, is showing also. Helium is very strongly bound, and it ends up being my clue to that lambda that would parameterize the change in the strong force. So I define a ratio, R, as the isotopes binding energy per nucleon divided by the alpha particles binding energy per nucleon. And you can imagine a small change in these two quantities, which I call alpha and I. I think, did my ratio switch? Oh, I did. That's just a typo. The alpha over I is correct, so this is the way it's shown. I wonder if that's in my paper. Oh no. Okay, so you can imagine a small change and define a ratio under A and D, like an alternate universe versus normally, and make some assumptions like the well is shallower during A and D, that is related to those absolute values, and then do a little Taylor expansion magic, because small changes and so forth. And finally, in the end, you can infer that the ratio during accelerated nuclear decay is going to be greater than the ratio normally for potentially for some of the nuclides. So come back with me to beryllium-8. It's an alpha nuclide. It should be like 2 alpha particles. Surprisingly, it's not stable. It's very, very, very unstable. It immediately becomes 2 alpha particles. I kind of think that the critical value for this ratio that might take you from one phase to another, switch phases with the tweaking of the strong force, would be less than beryllium's R. Because I think beryllium might be the only nuclide that might be in that other funny phase normally. because all it wants to be is alpha particles. And I'm imagining a liquid of neutron and proton pairs. They're like ions, so it's like a molten salt. And sometimes they get together for a period of time. A couple are close together and form kind of a molecule. They dimerize and give you an alpha particle enough to tunnel out. But that's the normal phase. Then this other phase would be like all alpha particles. And so beryllium would fit that category because it immediately becomes 2 alpha particles. So this is a graph of the ratio calculated from the binding energy curve. And it starts up with, now at the top, with helium, beryllium going down. Alpha nuclides are shown in that pre-saturation piece. And then I've also blown up the scale so we can see these small changes. Notice that the ratio is 1.05, 1.95, so it's a pretty blown up scale there. So my idea is that during accelerated nuclear decay, this ratio is going to look different. And now the tail end where uranium-238 is and so forth is up higher comparatively, and it would be just those tail end neutron heavy unstable nuclides would be in a different phase. And so just summarizing, because my model again, I showed it, so I can back up one more. Just the formation of the halo with the heat being sucked into the middle as the alpha particles are going out in their little sequences. And the heat sink is occurring because at the end of the decay chain, the stable lead-206 is now underneath that critical R value, and so it needs to be, its natural phase is no longer this higher entropy phase that characterizes the unstable nuclides during A and D, and so it has to go back to its natural phase, which is the liquid drop, condensed matter, the neutrons and protons as cation pairs as cation and ion swimming around, and that is the heat sink. So just to further summarize, just repeating the points of previous slide, it's like ice cubes cooling a beverage in the melting of them. If the nuclei of heavy, unstable nuclides like uranium-238 and thorium-232 are in a lower entropy phase during A and D, due to the tweak in the strong force that accelerates decay, and if there are no thermodynamic considerations associated with the miraculous change that these nuclei just find themselves in the lower entropy state when AND is switched on, and if the decaying nucleus undergoes a spontaneous endothermic first order phase transition, entropy increasing, once it becomes lead-206 for uranium series or lead-208 for the thorium series, and abruptly ceases to be unstable. And so to model, I need help and insight and research what to use for V2 and V3 in that Stillinger-Weber-like potential, which is commonly used in molecular modeling. So if you have any ideas, I would love to hear them. And also the big outstanding problem with my solution is that how does the heat get back into the nucleus? I've explored black body radiation, and that doesn't work. I'm wondering if there's some kind of Bremsstrahlung, which is breaking radiation. I think it has to be radiation. It can't just be the bumping around, which is how in the kinetic model of conduction of heat, we think of it. Particles are moving faster if they're hotter, and so heat is conducted or moved from here to there by bumping particles around with collisions. Well, that doesn't work for understanding the temperature or characterizing the temperature of the nucleus even. So that's my big question, and also would love any thoughts you'd have there. If you're an expert on bremsstrahlung, please help me out. So that's just a picture of an ideal gas bumping around where the speed of root mean squared speed of the particles characterizes or gives the temperature. The red ones, just so you can follow a few. But that's where I will close. So my talks have nothing to do with birds or monkeys, but that's the cover of the CRSQ journals that my articles, parts 1 and parts 2, were in. I have my own copy here. But like I said, I have copies of my papers, like 20 of each, which looks like it's enough for those who are here tonight, out on the table, and you're welcome to take one. So thank you very much for listening to my idea.
Thank you, Barbara. We will now open the floor for questions and answers. So if you got a question, let me know and I will get a mic to you. So before you ask the question, be sure you got a mic in front of you. So with that, we will be also passing baskets around for donations. Just a reminder, Rocky Creation Fellowship exists only on the donations of happy customers, and we are completely 501c3 nonprofit organization. So any donation you make, if we know who you are, we can send you a tax-exempt receipt. And so with that, let us begin with questions.
Okay, Barbara, I understand the heat generated by the slowing of the alpha particles. Is there any heat associated with the recoil? Physics says for every action there's an equal and opposite reaction. And the nuclei left behind after ejection of an alpha particle would have some recoil, but it's obvious that based on masses, it wouldn't be very much.
Right. For sake of simplicity, and even for an underestimate, I just used that Q sub alpha, which is the total energy associated with the alpha particles themselves. But yeah, there is energy with the recoil. You can include that, and it's a slightly different number. I think it's called E alpha for the alpha decays, or then you have a Q beta and E beta. You can add up all the energies associated. You can do that very rigorously, but I don't bring it in simply because it's just an order of magnitude calculation, that adiabatic temperature rise, that it's just huge, and so we have a problem. But to get an order of magnitude, that about an MeV per alpha particle thing from there, but definitely a lot of slosh, definitely not a lot of detail in the heat analysis, but it was more of order of magnitude sort of approach. Yeah, related to that, the temperature rise for an entire pluton that's given in rate volume 2, Dr. Snelling had a friend of his make an estimate, and heat calculation was like a temperature change of 22,000. So my numbers were very conservative compared to that. So that's because you know, every little radioisotope that's out there in the rock, in an inclusion, not an inclusion, if it undergoes decay, there's heat being generated. If decay is accelerated, the heat is being generated quickly, and this, just so you understand, this mechanism is not limited to radio halos. It would, wherever the lead finds itself to be, probably close to wherever the uranium was to start, will be a heat sink. So it is more broadly applicable than just radio halos. But radio halos give you just such a tangible picture and realize that you need that. It's also concentrated and you need that sink right there, and the cooling needs to be happening while the alphas are going off. That's the reason why the halos are so important to my presentation.
Okay, any other questions? All right, well, while you all are thinking of questions, referencing your lists of questions that you have, I referenced my list. I have a question.
Yes.
I was unclear on your discussion about the instability of the beryllium nucleus.
Okay.
I was under the impression that that's typically a stable nucleus, but you're saying it's highly unstable, meaning it's not radioactive though, is it?
No, beryllium-9 is the usual stable nucleus. It has an extra neutron.
So beryllium.
Beryllium-8, which would be one of these alpha nuclides, all of which are very stable otherwise. Helium-4 is the alpha particle. It's intrinsically very, very stable. Carbon-12, very stable. Oxygen-16, very stable. It's beryllium-8 that's highly unstable, which is surprising in a way because it's one of these alpha nuclides. So that seems like it's just a pair of alpha particles, but it's highly unstable. I brought it out in my Foundations article. There's a paper I ran across of astrophysicists who postulated some alternate universe where the nuclear force would be a little bit stronger instead of weaker, and beryllium-8 would stabilize, and the nucleosynthesis of stars would proceed more easily in that universe, and there would be more habitable planets and more evolution. So, but anyway, it's that AU idea is it's interesting to think of a miraculous scenario, a change in the strong force, as kind of like an alternate universe because it's slightly different forces or strength of the nuclear force.
Okay, but in this universe, you got to have 5 neutrons in the beryllium nucleus for it to be stable.
You got to have that extra one, yeah.
So when you say it's unstable, then the tendency is for it to split quickly after its formation into 2 alpha particles?
Its half-life is minuscule. I'd have to look it up, but fraction of a second. It's just, seems like it's almost immediately 2 alpha particles, which is that idea that it's already in this phase. And the problem is, how do you talk about the phase of a material when it only has 2 particles, 2 alphas? And so it's really, you can only sort of start thinking about the nucleus as being a goop with a phase and properties based on the number of particles interacting with each other when you get to these big heavy ones. That pre-saturation region on the binding energy per nucleon curve, it's kind of like before you become a fluid. It's that flat top region of the curve that you would say is where now we have liquid nucleum, or no one uses that, that's my own term. But so that's why beryllium-8, it's beryllium-8 that's unstable. So.
All right, so we need some more questions.
I need ideas.
Questions. Okay, we need some ideas.
Yeah.
All right, anybody have any suggestions to help launch her model forward?
This is just a question not to help your model progress. I had heard a long time ago that the existence of these radio halos showed that God quickly froze things as he was creating the earth. I think you're saying that's a true statement, and you're showing that it's the ice cube, the cooling with the heating that's causing the halos to exist. But Why is that important? Why do we have these halos, and what would happen if we didn't have these halos?
Okay, so to speak to that, the original thing was that halos were only found in Precambrian granites. And particularly the polonium halos are problematic because polonium is so short-lived that it would have to have been primordial. But that doesn't work either, so it's like God put the halos there almost like a fingerprint. That was the argument of Robert Gentry with the book with the halo on it. But he did not realize that radio halos were also in rocks associated with the flood. And so Dr. Snelling devised a model to explain polonium halos via accelerated nuclear decay, whether it's an episode during creation week or an episode during the flood, depending on whether your halo is in Precambrian rock or associated with Phanerozoic rock. And it's this realization that the radon, which is one of the, radon-222, one of the radioactive nuclides in the cascade, is a noble gas and it's slippery and it can escape the zircon housing the uranium that would otherwise contain all of the subsequent decaying nuclides in that one spot, and so you get all the concentric rings in one place. But if the radon can escape and then it decays somewhere else to polonium-218, and that aggregates, it's a collection site of some kind because of affinities. There's sulfur there, the polonium wants to go there, for example. Then you can collect enough that will create a daughter halo separate from the uranium halo. But it was the inability to explain the polonium halos that caused this idea that maybe they were just put there as a feature of creation. But that would not be what would be considered reasonable given that they're found in granites associated with flood rock, that there had to have been a way that these actually formed.
I'm not sure if I can ask the right set of questions based on some of the assumptions, but can any of this be associated with how we get power generation out of a nuclear reactor? We have a traditional nuclear reactor where we do, get the reaction. You have to have the heat generation that heats the water into the steam and runs a turbine and so forth. Those are sort of old style ones, and they're doing that. But supposedly in the next 5 years, we'll be able to come up with some nuclear reactors that can get away from some of that and actually consume the additional fuel. And is any of this anywhere close to being similar to what you're talking about? As far as the formation of the halos in the granite, there has to be a heat transfer that's going on.
Yeah.
And you have an external heat transfer as things cool down, something like that. It's sort of like on a peripheral. Is it just kind of approaching this in a whole different direction than what we look at when we're looking at like a nuclear power generation system, but not that much different. It's just a different way of categorizing the power and how we generate it through heat transfer.
Certainly, you have heat generated with nuclear power. That's kind of the point, like you said. But there's no cooling mechanism intrinsic to the decay process itself with nuclear power. You externally you cool it with lots of water, but what I'm arguing for is an intrinsic cooling mechanism within the nuclei that decay, that then becomes its own heat sink. So I don't. But the one connection do see is that you can find all kinds of interesting things about molten salts these days just by Googling it, because that's a big feature of the direction nuclear reactors are going somehow. I don't know myself exactly, but there's a particular salt called fly, but that's very important to that process. So I was looking up salt stuff and ran across that, but I don't see an intrinsic cooling mechanism in nuclear energy like I'm talking about.
Well, I think what you're talking about is you're basically talking about heat generation, and the halos are forming from that as you kick off the neutrons and they go out in the sphere, in the material. And that material there is maybe is a little bit cooler, but that forms the halos that we see.
It's a burn mark, yeah.
It
deposits the energy, yeah.
It deposits the energy as a burn mark.
Yeah.
And it's a way of looking at that kind of thing. So I'm trying to associate that with an overall thing, and then kicking it back to like whether we use molten salt to take and cool stuff, or to take and hold energy and then take and use it, being able to transfer the heat so that we run a turbine or do some
Right.
things like that.
Yeah. So in my case, the salt thing is just purely an analogy of looking at a molecular system, a molten salt, which is cations and anions interacting, that you can model that. But the interior of the nucleus is what, it has a phase too, and that's a weird idea to get your mind around. But that is what I'm making an analogy to salt with. But in my presentation, salt doesn't come into play except by analogy to figure out what would be, if the latent heat would be large enough potentially to solve the heat problem.
Dr. Burke, when you talk about phase changes in the nucleus, the fundamental characteristic of the nucleus doesn't change as far as a condensed matter during that transition, right?
It changes. Some of the isotopes would be in a different phase with this change in the strong force.
How would you distinguish the phases from each other?
Well, I think that ratio of the nuclear binding energy for an isotope to the nuclear binding energy for an alpha particle is kind of the key. That a breakover at a value of about 1 might characterize this other, being in this other phase. And this other phase might be a collection of alpha particles forming that liquid instead of a collection of neutron-proton pairs. If they all paired up, and that was a new, instead of a few of them occasionally pairing up, but they all paired up, and so now you have a soup of alpha particles in at least some region of the nucleus, because anyway, that's the idea, that this other phase. And so beryllium-8 happens to have, it's the only element with this ratio value normally greater than 1. And it is crazy that it's not stable when all the other alpha nuclides are. And it immediately wants to be 2 alpha particles. And so I'm seeing in that, except a very finite version, this tendency toward being a soup of alpha particles instead of a soup of neutron and proton pairs.
So it's like an alpha particle is an island of stability onto itself.
Yes.
And that's low mass.
Yeah, and that's what that, this has really just caught my attention so much in the nuclear binding energy curve. If you zoom in on that little helium peak way over on the left, that's what's shown on the right, helium is just way more stable than the neighbors as you're building up larger and larger isotopes moving through the periodic table, basically. So that caught my eye, that something might be important to compare like I have up there, though I think I have it upside down, the binding energy per nucleon of the isotope versus that of the alpha particle. So,
Okay.
what was your question again? I got lost in myself.
Well, just the impression that beryllium 8 seems to present an island of stability at low atomic mass for such a light isotope compared to carbon 12 and then oxygen 16 and then on up to calcium 40.
Yeah.
So,
Yeah, so what's interesting is that bend over on that top that we're dropping back down in this presentation. And it's way over there that a few unstable isotopes are included in this curve because they're so long-lived. You know, they're almost stable in that sense, U-238. And so when you flip it around and graph this ratio instead, like I did, you can imagine a different shape to the curve that would put those tail unstable nuclides up above beryllium's value and potentially in this other phase. So it's not like all the nucleum for every isotope would be in this different phase. Only the long half-life, big neutron-heavy nuclides that undergo these decay sequences. There are really only a couple that are significant geologically, the thorium and 232 and uranium 238. It's not like they're a whole bunch.
well, I think because of the complexity of nuclear structure, I think that the idea of distinguishing phases is much more complex than in the physical world, in the macro nuclear world, where there's gas, solid, liquid.
Exactly. That's why even if I manage to model something, you know, the question then is, how does that really relate to the nucleus? But it's really crazy how well the liquid drop model works. It's really crazy how well the shell model of the nucleus works. Neither of these should work, and yet it seems to be a very semi-classical system, even though it, you would think it would be quantum. I think more quantum, but you see the fundamental strong force is the quarks glued together to make the nucleons. So nucleon-nucleon interaction is a residual force. And then you get to, that I think is what allows it to start almost behaving classically, just like with atoms and molecules. The atom is, we describe quantum mechanically the interaction between the nucleus and the electron, but then the residual forces, hydrogen bonding, van der Waals, all those things in the molecular world, then we jump to classical models, classical molecular dynamics, and it works. So there's a similar analogy there, that because what we're modeling is really the residual force of the fundamental force, it blurs things out, kind of. In a way, it's related even to my Ph.D. research, which was how does washing out quantum effects by connecting it to an environment. There's a funny relationship there, but does that make any sense at all? Okay, thank you for.
I did want to mention real quick that when you're talking about Bremsstrahlung radiation, are you seeing anything in the literature regarding alpha particle impact within that sphere of a halo?
That's what I don't know much about and want to explore more. Usually Bremsstrahlung is, which is a breaking radiation, is significant for electrons, and it's not so significant for alpha particles, which are so much heavier and bigger, but it's not absent. And so those alpha particles come to a halt, serious breaking of a charged particle, and that would emit some radiation. Because I think it's radiation, light, has to be how the energy gets back into the nucleus versus bumping around.
Right. Well, I could see that electrons could be involved inside the halo as well, especially if nuclear weak force is in play, because you have electron emission in that.
Right.
And
Yeah.
so there would be possible bremsstrahlung feedback into the nucleus.
That's interesting. Yeah, it's really interesting. That's a good point. I'm ignoring them from the standpoint of the heat that they make, but I maybe shouldn't be ignoring them from the standpoint of the bremsstrahlung. Thank you. Wow. Yeah.
Okay.
That's very cool.
So I'll leave it at that.
Okay.
So Barb, this is a question from a YouTube listener.
Yes.
If nuclear decay could be accelerated now, would that provide good opportunities for your research?
If you could actually accelerate nuclear decay in the same way that God would have done it, then you could observe a halo form, and then the polonium halo as the daughter, and, so we would have all this proved out. That would be really great. But I think the problem is that my model is tied in to what would be happening internal to the nucleus because of the change in the nuclear interaction that would be brought about miraculously. But it seems like there would have to be some way that it would help me. So if you have an idea on a decay accelerator, I know we can strip all the electrons off of stuff, like with the osmium, and suddenly, if you want to go make yourself a plasma, you can accelerate decay. But I'm not sure how this would help, but it would have to, so. Thank you, question asker.
Okay, any more questions? All right, so I have another question which I think got blown out of water when you were answering a previous question, saying that there seems to be I don't know, like a changing from quantum effects into classical effects under certain circumstances. This may already be moot at this point. But the question really had to do with the energy getting back into the nucleus. And what I'm wondering is, would the energy have to enter back into the nucleus through some sort of a quantized amount? Like, the electron shells, you can only affect an electron's position through a quantized amount of energy, either coming into the electrons or moving out. Does a similar sort of thing occur with the nucleus?
Right.
Where you need to have a quantum effect so that your energy coming into it would have to already be a quantized amount of energy, like a particular frequency or a particular size particle or something.
Right, I think that would reduce the efficiency of any spectrum of radiation, because only certain photons, if you will, would be absorbed. But this is how far I kind of went down that road, and I put this slide after my talk because I thought I'm not going to get there anyway. But this is the energy level splitting when you model proton and neutron wells. This would be the quantum model, but it's still a residual force. Anyway, you have these energy levels that I'm imagining during and after accelerated nuclear decay. If you switch from the classical model to the quantum model, now you have a bunch of energy levels, and they're all in a slightly different place. Slightly moved up, slightly squeezed or stretched, the whole set of energy levels. And so for that energy to get back into the nucleus as photons, it would have to be a spectrum, but there would have to be the right ones that would make those little shifts. Those are my little squigglies, the reds and the yellows. But this is how I eliminated black body radiation, because the temperatures are way out of line to provide the right energies. These, like a quarter of a half or half of an MeV or something might be what we're looking at here. Because it's an MeV per alpha particle, but these are individual neutrons and protons, so there are 4 of them, so that's where I get a quarter of an MeV. Might be the amount of energy, rough, approximately, to shift your energy level to the other phase. It is a headache to switch from quantum and classical models, for sure. But.
Well, so I guess part of that question is it reasonable to think that the quantum model could be actually operative there, or is it more likely a classical model?
It's all of them, and that's what's so crazy. Let me go back to that slide. It's just, where's my slide? Okay. So, back up even one. The liquid drop model, purely classical. Particles bumping into each other in a liquid. Or classical in the sense that like molecular systems are as a residual. Or then we go to the full-on quantum shell model with the Pauli exclusion principle at work, because the neutrons have opposite spin, and that whole business, the protons have opposite spin. That's why they 2 per energy level. And then the alpha particle model on the right describes the escape via tunneling of the alpha particle, and that's a semi-classical because you have a Gaussian wave packet that escapes according to the usual calculations. Anyway, it's like all 3, and they all have merit, and it's very strange. So it makes it difficult to well, it's way easier to do classical physics than quantum physics, especially if you go all the way to the fundamental force with the quarks interacting, and the gluons. That's quickly, is mind-boggling. So I'm leaning on the fact that there's so much evidence for classical behavior inside the nucleus to come up with this model. But it very well might be a quantum argument is required as soon as you get into photons to get the energy back into the nucleus. So.
Okay, and one other question, unless there's somebody out there. Oh, okay. I'll follow up later.
This is just a follow-up. This is a follow-up from the guy on YouTube, or guy or gal. In 2009, ICR reported in X and Facts that an Italian physicist used cavitation to accelerate the decay of thorium-228 by 4 orders of magnitude. His question is thorium-228 decay acceleration something that you could use?
I need to look into it. I don't immediately see how. I think it's generally very interesting to see that there are many ways in which decay can be accelerated. And there have been ideas that neutrinos can do it, ideas that piezoelectric effect can do it, this, stripping off of all the electrons ionizing, so you have a plasma that can do it, so that it pulls it out of the realm of, well, that's ridiculous. These are constants. They're not. So that's useful, but it's more of a generic utility than in my research. But would you just read the question again so that
Sure,
then
the question, yeah, okay.
So I can make a mental note?
Is the thorium-228 decay acceleration something that you could use?
Well, I'm glad to be, I think I ran across that at one point, but I'm glad to be reminded of it, and will read up about it, and it might help me.
Okay, then I guess it kind of reminds me of something, so I'll ask a question. So there's a laboratory in the Ukraine in Kiev, and hopefully it's not destroyed.
I know.
And, yeah, and their electrodynamics research lab And they've claimed that since February 2000, there's been all kinds of experiments that accelerate nuclear decay and get a lot of the components down to, my eyes are going bad, by producing traces of all known chemical elements and their stable isotopes. And I think part of it, and correct me if I'm wrong, I know some of this research was using like incredibly high voltages.
Yeah.
So anyways, that was just one that I was aware of.
Right. It's hard to envision what would be going on geologically to replicate those experiments that accelerate nuclear decay that would be consistent with Noah and family and animals on an ark floating above the water. You know, that's part of the reason I tried to get rid of the heat, because I know sufficient squeezing, stress causes things, but that also is not a feasible state of the Earth for that to be the explanation for accelerated decay, I think. So it's I guess my focus here is not how to bring about accelerated decay. My model happens to assume the strong force tweaking, but I don't think you get rid of the heat problem by coming up with a naturalistic explanation for accelerated decay. And that's kind of the point I made at the very beginning, that the heat problem is there. Evidence of the heat is the halo itself, or any fission track you see in the rocks. The heat was generated. Even if there was something that makes the totality of the flood event somehow in an energy balance, so that some stuff took heat and some stuff gave heat, that doesn't fix the details of the halo. A generic freeze that brings everything to absolute zero prior to is not going to fix it either, because the temperatures associated with the stopping of the alpha particles, the 500 million of them per ring, is going to raise the heat locally and anneal the thing away, or or vaporize the region even. So certainly melt it. So I guess that's my point. The heat, one of my main points was the heat problem is there because the radio halo is there, and the solution to it is narrowly defined: contemporaneous, commensurate, and the other one I said local. And so a generic freeze, that like Dr. Humphrey's first idea that he put in a rate for getting rid of radiogenic heat, was an expansion of the universe, because that would cool things. But that's a generic freeze, and the oceans would freeze. You know, Noah and everybody and the animals would freeze. So you can't have a generic freeze. So then his newer mechanism involves black body radiation, and you have this temperature to the fourth power. So the efficiency of cooling is greatest for hot objects, and so that's how he defines that models, such that the animals and people on the ark don't die. And then that dictates what he can do with his critical angle for total internal reflection in the fourth dimension. So that cooling mechanism is trying to get at that idea that it's got to be local or commensurate. I'm not sure which, I have to think about it. But a generic freeze, or even the fact that there's an overall energy balance, still does not solve the heat problem it doesn't, as I see it. Does that make any sense?
Yeah. Not sure it does for him. I mean, I kind of understood what you're saying.
Oh, I thought that was your question.
Well, the last.
I'm sorry.
Well, it was kind of combined. The only thing I added was I was aware of this laboratory that's able to
Yeah,
accelerate
Ukraine,
nuclear
yeah.
decay.
Yeah, I'm aware of that too.
Yeah.
Is there another question?
No, there isn't.
Thank you for that question asker.
Any other questions?
I'm going to go out on a limb and make a proposition that the sudden appearance of radio halos was a result of the fall and the decay of all things.
That would work for the radio halos that were in the Precambrian. But you have these granites that, in the molten state, radio halos can't exist in a molten state. And so the granites, if they are cooled magma that is layered between or associated with flood rock, now you have to explain the radio halos in the flood rock. But perhaps there was something with the fall instead of day 2 of creation. Maybe it was a miraculous intervention, whether accelerated decay or not, that put those radio halos in Precambrian. But the problem is the Mesozoic and Paleozoic and Cenozoic granites and their radio halos, which is all flood rock.
And are you able to distinguish between the pre-flood and the flood radio halos?
Just by geology, that they for the dike, for that granitic rock to get up where you have sedimentary strata, that has to post-date that strata. So the strata was laid down, then it forced its way up, and so it's after. But there were no radio halos in it because it was molten. Then it cools, and then the transport model, due to Dr. Snelling, that explains radio halos, is tied in with the crystallization of the granite as it cools too. So that would be how you can distinguish. Just by location in the geologic column, you can say whether the granites are flood granites, if you will, Phanerozoic granites, or creation granites, or fall granites, like you say. Yeah, that's one we forget about a lot, I think. We forget about the miracle associated with the fall, when suddenly death came into the universe and clearly brought about miraculously by God's will and judgment, not gospel, except for Genesis 3:15 with the promise of the seed of the woman, right? We have that proto-evangelium.
Okay, I've got another question if nobody else has one. Actually, 2 thoughts. First, in regard to the radio halos in both the intrusive granites and the Precambrian crystalline basement granites, could it be that if you are hypothesizing that the Lord changed the nuclear strong force, and that's what was responsible for the radio halos in the intrusive granites, could that also be the explanation for the radio halos in the Precambrian granites as well? Just the whole kit and caboodle, that i.e. that there were no radio halos at the creation or even at the fall, that they all appeared as a result of this change in the nuclear strong force at the time of the flood.
The only reason why you would postulate 2 different episodes of accelerated nuclear decay is that the cooling from the molten state and the crystallization of the minerals around the zircon grains with the inclusions is all part of the model, the transport model, to explain the existence of polonium halos. So that would have to have been the case with those pre-Cambrian granites would have to have been molten state, which you can sort of imagine maybe day 2. And that's what Dr. Snelling has done with the day 2 is when the dry land appeared, and so he postulated that that might have been day 3. Do I have my wrong day? Thank you very much. Sorry. So what was day 2?
That was the separation of the waters below and the waters above the firmament.
Yeah. I don't want to misspeak. So it was one of those days that Dr. Snelling argues where a lot of geological work was done. It seems to me like it's
That would be day 3.
Day 3, yeah. So that there might have been a reason in creation on that day to have another episode of accelerated decay. But it's because the molten state and the crystallization and the expelling of the water as the rock crystallizes is part of the explanation, and the only one that's out there, of the polonium halos, that you would see it as another accelerated nuclear decay episode.
Okay. Switching gears, another question. Again, if you invoke the divine intervention to change the nuclear force, and going back to that model that we were discussing earlier, where you put up the slide that wasn't part of the show but was a later slide that showed the nuclear energy levels having been all bumped up, some
Squeezed, bumped up something, yeah.
Yeah. Would there be any, and this goes back to your question about, how can you advance your model a little bit here? Could it be that whatever it was that bumped up the nuclear force was just perhaps like a wave going through or something like that only happened for a short time, and those energies that you're showing that were bumped up a small quantum amount almost immediately bumped back down again, so that that would change your quantum model a little bit? Would they then be able to receive these energies back into themselves as a result of that? So
more of a naturalistic explanation for accelerated decay, like a neutron, like a neutrino wave or something. Is that?
Well, I mean, it wouldn't have to be a naturalistic explanation for the decay itself.
Okay.
It could just be simply if God caused the nuclear force to change, of course he had to change, would make it change back, or else we wouldn't see the nuclear force that we see now.
Right, so
if he changed it back immediately, like he released it just long enough to cause the radio halos and stuff to begin forming, and then suddenly changed it back to its normal, would that change the quantum state of the nuclei back to something that would simply be able to reabsorb the energy?
Right. Yeah, or even where I'm thinking from what you said is it could just be a big giant kick, and then there's a relaxation effect, and all of the episode is really the relaxation process back to the normal state. It would be just a different way of thinking about it. But I have to think about that, whether that helps get energy back in the nucleus or not. But that's a good thought.
All right.
And I will think it.
Just thought I'd throw it out there.
Yeah, because that's a lot of times we knock a system out of equilibrium, if you will, and then it takes a while, it rings or whatever it does to get back to where it was, so that maybe the episode of accelerated nuclear decay is really just a relaxing back somehow. That's altogether different from what I've thought through, but it's interesting.
Okay. Any other questions, thoughts, comments? All right. So I guess that does it for talk, unless, oh wait, we do have another question. Just a second.
I have two questions. One is, what is the shape of the halos, and how well can they be observed?
Okay, they're spheres, but they're spherical shells. So when you cut them in half, you get rings in cross section. So I have some slides that would explain that I hid, and I'll hide, and I'll show. That might help. This one in particular. So that cage, that spherical cage, that would be what a halo looks like from the outside, just a sphere, especially if it's polonium-210 halo, because it's just a single alpha energy emitted before you get to stable lead-206. And the way they're seen, it's really crazy, is because they happen to be, at least the ones that we can see or notice, are in mica. And mica is these flat, like natural thin sections. And so the way they were mounted and photographed was with Scotch tape, by peeling off one layer at a time of the mica, sticking it under a regular microscope, because these are in the micron range, they don't need a special atomic microscope, and looking, and you see them, and they're little circles in cross section. You have to be careful when you peel them off to get the, you peel through an entire halo, and it's only the largest, the sheath on your Scotch tape with the largest ring that's the great circle of the sphere, just like cutting at the equator, because then that radius will characterize the energy of the alpha particle that made the little mark, that many of which finally gave you the full spherical shell. So there you see on the left what mica looks like, right? A bunch of natural thin sections. And there you see the fancy, sophisticated material for separating and mounting. I have a whole stack of mica sitting in my house in a little bowl, and Scotch tape and a microscope ready to look for them myself, and I've not gotten around to it, but that would be fun. I think they're pretty ubiquitous. I think it would be pretty hard to not see them in granite samples.
And my other question is, I'm just curious, it might be a silly question, but just how round are the halos?
These are actual photos. That's an actual photograph of a radio halo in the cross section of it.
So are they approaching a perfect circle in some cases? Pretty close. So the degree to which they're not a perfect circle has to do with the shape of the lump of uranium that's in the middle, the inclusion it's called. So you have a little lump of uranium, most of which is U-238, and it's, if it were a point in the middle, you get a perfect sphere, but it's whatever it is, some little misshapen blob. Everything is approximated as a sphere by physicists, but to the degree to which but what that does is it smears out the rings more than it distorts the sphericity of it. It just makes those rings blurred, because some of the little burn marks are from a uranium that emitted that was a little bit to the left of the center or a little bit to the right of the center, but on average, with the 500 million decays making a single ring, what that does is it just blurs the ring out a little bit. And if it's overexposed, as it's called, because there's just too much, the uranium inclusion is too big, it just smears everything out. You don't even really see a halo at all. So it's captured, the size of the inclusion is, you can even put parameters on how big of a inclusion of uranium will give you a nice halo versus not.
And then the last question is there any relationship to this phenomenon with Luke 19:28 to, what is it, 19:28? It says, if they keep quiet, the stones will cry out.
Sure. Right, I mean, that's that beautiful metaphor that we can look at the rocks and they are telling us that there was an accelerated nuclear decay. Part of that argument is Dr. Humphrey's work with the diffusion age of the Earth based on helium and argon he found in deep zircons or was found and measured, and he was able to date the Earth that way. So in that sense, the rocks are speaking if studied properly, and they're telling us that the Earth is the age the Scripture says it is. So, amen.
Awesome, thank you.
Sure.
Okay, we've got bunches of more questions here.
Are the radioactive halos restricted to the biotite mica, or is it also in the muscovite?
It is found in other materials. There have been radiohalos found in diamonds, even in coalified wood, remarkably. So no, they're not limited. They're just particularly findable, visible when they're in the mica because of those natural thin sections. So they're not limited. When the uranium is enclosed in a dense material like a gem, a zircon, I wear one, by the way, my husband gave me, my necklace, it's a zircon, then the products, the daughter products that are still radioactive can't escape readily. And so then you get the nice rings with like all 8 of them for uranium because nothing can go anywhere except for that radon that can escape. And so some of it escapes. And so you can get the displaced halos because of the slippery noble gas of radon. That's the model anyway. And here's a really cool thing I happened upon. So thorium, there are thorium halos too, thorium-232, and poloniums are in the chain for thorium, but there are no polonium halos that correspond to those. And if you look to see its radon, it's a different radon, its half-life is too short. It doesn't have time to escape. So it's the absence of those polonium halos and only the polonium-214, 218, and 210 associated with uranium-238 is itself a ratification of Dr. Snelling's transport model. It's really cool. It's that you don't get those separate polonium halos for the thorium poloniums, but because its radon is too short-lived, like seconds or something. So.
I've seen some rock, different kinds of rock. I'm not real good at identifying particular types. Like granite's maybe easy, feldspar is easy, some of those type of things. But I've seen mica in rock, different rock pieces that I have, and it's kind of like your last slide that you just showed just prior to this one, where you have the mica stuck to the tape. You have the orientation on that mica is the same kind of orientation that you may see on some of these rocks. As you take and spin the rock around and you look at it, you can see mica is going one direction, like the top left corner. The bottom right corner, the mica is going a different direction. You see that orientation all the way around in the rocks. That's how that gets into that position inside a piece of solid rock. is kind of, would be kind of amazing. So it introduces a question with that. Sticking that to tape and then looking at it under a microscope, I can figure, well, that's easy. That all of that mica can end up being orientated a different way. I back up to some soils that I know of, but the soils, sometimes they're held, when they've been deposited, they are actually deposited, you know, kind of like in small layers, just like that mica, except they're touching each other at different angles. There's void space in there, just like you see in that mica picture. When you take and withdraw the water and you allow that to compress, allow it to take and fall together, all those things kind of come closed and you end up losing all that space. You'll never gain that space back unless you find a way of pressurizing, put pressure inside that to take and push the mica apart, push the rock apart.
Right.
So that's a real, to me, that's a real interesting picture, and it's kind of akin to how you cut cross sections in that sphere. It's the same kind of thing.
Yeah. Well, that is why the formation halos is connected to the actual crystallization or cooling of the granite, because you have the void space of the water forcing its way out as part of the cooling and crystallization process, but then you don't get it back.
Right.
Yeah, that's why radio halos wouldn't just form in already cooled, compressed Precambrian granite, right? It has to have that molten void space, water flushing event to move those poloniums. So.